All right, guys, today's lesson is a continuation of what we started yesterday and the day before with our our experiment looking at whether or not the row you sit in impacts or causes you to have a higher or lower score. So I've put some of the initial information here, and we have our line of best fit that we found the other day. We have our slope of negative 1.52. And remember that here that this y hat, the y predicted, is the predicted value of the test score, and x is the row that you're sitting in. Okay, so row, and this is our predicted test score. So just to make sure we understand and remember the context here. So another thing I'll point out here that we would get from computer output is the standard error of the slope of a 1.33. And we're going to see how we will use that here in just a minute as we look at confidence intervals. So what we're trying to do here, if you'll notice number one, it says if we were to take another random assignment of 30 students, do you think the slope of the least squares regression line would be the same? And of course, that would be no. Because if we did this over and over again, we have this natural variation that occurs from sample to sample. Every random assignment will give different results. Okay, so if she randomly assigned the students to different rows the second semester, it would get different results. Excuse me. So what we have here is we have this variation that's going to occur. So even though we have this line of best fit, we recognize that the values in that line of best fit will vary. So what we want to approximate here is we want to find, in our case, a confidence interval for the slope of this line of best fit. So as we saw yesterday, we're going to use this beta, looks like a capital B, as the true slope of our population least squares regression line. And our statistic is our sample slope. Okay, and as we mentioned, that B, the sample statistic, in our case a negative 1.52, is going to be the point estimate in this formula that we've used a couple of other times when we did confidence intervals, the point estimate plus or minus margin of error. So how do we do confidence intervals for our slopes? Okay, well, the conditions that need to be met, there are actually 5 conditions for these, and it actually follows a little acronym, LINER, just think liner. So most of this is pretty simple to do, but first of all, we want to make sure that our scatter plot shows some kind of a linear relationship. And we see this one of two ways. We see the scatter plot itself, which in this case is not quite as obvious as a linear relationship. As you can see to the right here, I've put that in here. But remember, we can also do the residual plot, which if you recall, when you go to your stat plots on the TI-84 stat plot, remember of the choices of the type of plot, you can do that plot of the residuals. Okay, so on our TI-84, you can go and you can see this right here, the plot of the residuals. And thinking back to Unit 2, the key here is that we don't have a discernible pattern that still exists after we do our linear correlation. If we had a pattern, we would have to do some kind of a logarithmic transformation or something like that, or a power transformation to make it, to linearize it. But as you can see here, we have no discernible pattern in our residuals here. They're just scattered and random on either side of our zero residual. So that means that our linear model is a good model. Okay, so this one is linear based off of that residual plot and just looking at the data itself. So then we need to consider independent. And in this context here, we're dealing with an experiment. So we're not going to do the 10% condition or something like that. But when we're doing in an experiment, because of the random assignment, we consider that each observation that we make is independent of the next observation. Okay, so by randomly assigning them, random assignment makes each observation, which in this case would be each student, each observation is independent of the next. Independent of the next. Okay. So then this one is kind of a new one. This idea of, not the idea of normal, but how we're seeing it. Okay. What we're going to be looking at is the dot plot of the residuals. Now, we have the residual graph. Okay. But as we look at the different dot plots, or as the different residuals, and we look at the residuals down here, what we've done is we've made a dot plot of those values. So like this close to 15 right here is going to be over here somewhere. Okay. We made a dot plot, and this is similar to um, before when we just look and we say, okay, there's no strong skew or outliers. So the dot plot of the residuals cannot show a strong skew or outliers. So we see that that condition is met. Also, we have here the residual plot doesn't show a clear sideways Christmas tree pattern or some kind of a like you have a lot here and then kind of decreasing as we go. Okay, so we don't have this kind of sideways Christmas tree pattern in either direction. And what that shows us is that our standard deviation at any particular row is going to be about equal. Okay, so equal standard deviation. It's not changing as we go from side to side. And then finally, the randomness. We already kind of got this one, so this is kind of a 2-for-1 here. We have the random assignment by the teacher. Okay, so the teacher randomly assigned. So now that our conditions have all been met, we can go ahead and actually calculate the confidence interval. So we have this general formula. The more specific formula that we're going to use here is that our confidence interval is that point estimate, which we already mentioned is the B, plus or minus our margin of error. Well, the way we're calculating margin of error is T star, and this is the same way using table B and our degrees of freedom that we did before with our confidence intervals. And we're going to do T star times the standard error of B. This is where that's coming into play. Okay, so I mentioned T star from table B. We're going to use our degrees of freedom equal to n minus 2. Okay, so in this case here, we're going to have 30 minus 2, which is 28, because there were 30 students. And from that, if we go to table B and we look at the 28 degrees of freedom, and we're wanting to find a 95% confidence interval, if you look down there, remember 95% confidence interval means that each tail is 2.5%. Okay, so each tail make sure you are taking that into account, is 2.5%. So if you look down that column, the tail probability 2.5% down to 28 degrees of freedom, you're going to get your T star equal to a 2.048. Okay, and you can look at your own table to confirm that. But then that allows us to get our final confidence interval. Okay, so the confidence interval, the B that we had was a negative 1.52. So negative 1.52 plus or minus that T star we just talked about, 2.048, times our margin of error and the margin of, or sorry, the standard error of the B's. And we were given that up above as a 1.33. Okay, so we then are able to calculate there that our margin of error, the 2.048 times 1.33, is approximately 2.72. So we have a negative 1.52 plus or minus 2.72. And that gives us then a confidence interval of negative 4.24 up to a positive 1.2. Okay, so that is our confidence interval. So now we're ready to conclude. All right, what can we conclude from this? Well, remember, a confidence interval, we state our confidence level. And so in this case, we are 95% confident that the true slope of the population LSRL is contained or captured by in the interval from a negative 4.24 to 1.2, and we should use units of measure here. These are points per row. Okay, points per row. And one thing I'll point out here too, this isn't necessarily part of the conclusion, but it's a good thing to note here. Note that because our interval actually contains 0, that supports what we looked at in our initial analysis here, that it's plausible that there is no real impact. Okay, 0 is plausible. So that's what we had actually said based off of our simulation the other day. Okay, but here we have some better support for that. So as we think about this, just going through this whole process here, we state we are estimating for our beta, the true slope. We have some kind of confidence level. We're running a one sample T interval for slope this time. We check our 5 conditions, and then we do the calculations and make our conclusions. All right, so very similar to what we've done before, just a new context dealing with slope, and the conditions are really where this is going to be different. Okay, so take some time, try this with this check for understanding, and we'll see how you can do.